Hi there, this is Courtney, and my homework partner is Emmy, and today we're just going to get a little bit deeper on our introduction to Monte Carlo. So first, we want to just look at this whole concept of what does it mean to even evaluate an integral. And so we have a few questions here, and the first one is just like, what is the integral being evaluated? Are we looking for the area of the integral? Can't we just do the integration? Why are we even considering a simulation to find this area? And then we're going to talk a little bit about expectation and what that means. And so to answer these questions, I have a little example right here, a fairly simple one. And so we have the function f of x equals x squared, and we have it graphed right here. And so we are looking for the area under this curve. And the way we can solve for that is to take the integral, we can integrate that function. And so you can see here this is a fairly simple one. So we see that the integral of x squared equals x cubed over 3. And so if we were looking for this area, and let's say it was like from 1 to 6, we could plug those values in and solve for that really simply. But we can't do that every single time for every problem because there are some that are like way too complicated and we need a different method. So that's when Monte Carlo comes into place. And so Monte Carlo simulation provides an estimation for those complex problems and points us closer towards the precise answer. And so Monte Carlo provides us with an expected value, which is the long run average of repetitions of the experiment it represents. And so, for example, if we were looking at a 6-sided dice, the expected value in rolling it would be a 3.5 because the average of all the numbers that come up in an extremely large number of rolls is close to 3.5. And so moving on from that, we have a little bit more into what is meant by Monte Carlo is an integral estimation. And so we have this statement: we can estimate the value of any integrand no matter how complex the integrand is. So we're looking at like why that statement is important. And that statement is important because with simulation, we are generating random points as answers to the integrand and accepting the mean value or our expectation of those points based on their probability of occurrence. So this gives us our answer. So the next thing is that what relationships do integrations, probability density, and fissionable materials have in common? And those things all have expectation or expected values in common. And so that kind of moves us further into how we can use Monte Carlo to solve for complex distribution functions. And so you can use Monte Carlo to solve for those. And you can kind of think of it about like in this like visual of tossing sand out and then counting up the grains of sand that land within whatever specified boundaries you have. And so that's kind of how Monte Carlo works. You have a whole lot of generating of random values that you're kind of throwing out, and then the ones that fall within your requirements, you're going to take the sum of those, and then that's your answer. That's your expectation of that. And so then it asks, how are complex distribution functions related to the math behind of the determining of yields of fissionable and fusible materials? And so we can see that a Monte Carlo approach would be super helpful and important with a problem like that because those materials have a really, really random distribution of energy. And so there'd be so many different combinations and things that would be really hard to account for. And so simulation can be used to provide an expectation rather than checking every single possibility, which would be quite impossible.
All right, so for part 3, let's look at an example in MATLAB that can basically generate, look at an integral and be able to find an integral both through regular integration and through Monte Carlo simulation. So as you can see here, what we've done is a really simple integration here, though it's quite difficult to do by hand, but it's simple to do through MATLAB. What we're doing is we're doing a double integral of x and y of e to the negative 1/2 times x squared plus y minus 1 squared minus x to the y minus 1 over 10. All right, so we can do this normally through MATLAB. If we do the integral, the second two integrals of the function from negative infinity to infinity for the x values and negative infinity to infinity for the y values. And through that, we get a normal integration number. Through normal integration, we get 6.2911. Now, if we do it through Monte Carlo's method, what we do is we do 3,000 simulations. We can set this number as high or low as possible, as really would like. And we generate x random variables and assign it to the x value. We generate random variables and assign it to the z value, 3,000 of them. And then we end up looking at the equation itself. So in this equation, what we've ended up doing is, with Monte Carlo, we've looked at this equation. We've seen that it has a normal distribution integrated into it, so we factor out a normal distribution. So then what we're left with is the expected value, which would be a mean. So then what we do is we multiply in a factored out normal distribution times what our expected value is of what's left. And this is what's left of this integral after we've looked at and factored out the integration, the normal distribution, sorry. So then when we do that, we run this, this is what we come up with. So this is our mu value here, which is a Monte Carlo simulation of 6.2907. Again, this number will change based on really the number of n. If you get high numbers of n, this number will get closer and closer and less variant or less variable to 6.2911. So that's how you do an example through MATLAB of integration through simulation.